Good evening, people.
Good evening, ma'am.
Yeah, we will just wait for a couple of minutes and see if someone is joining.
Okay,
Yeah, thanks. So, what you are studying lately? You are doing your
ma'am, I'm doing MSc Physics, ma'am.
okay from
Bharatiyar University in Tamil Nadu, ma'am.
okay.
Thank you, ma'am.
I think we'll start. Let the other people join. Oh, uh, so today is the week 4 of the live interaction session of the NPTEL course Introduction to Atmospheric and Space Sciences. So last class we concluded the class by discussing the different forces that are relevant when we are studying atmospheric science. I think we ended up with, or we concluded with the Coriolis force. So today we will be solving a couple of problems related to the Coriolis force and a little bit of some thermodynamics related problems also. So just as a revision, we will just look at we did, we learned like Coriolis force is basically given by 2 omega cross p, where v is the velocity of the object and omega is the angular velocity of the earth, which is having two components um, along the k and j direction, along the z which is upward and j direction. It is given by omega is equal to omega cos phi j plus omega sin phi k. So these are the two different components of the Coriolis force that is acting on an object which is at a latitude phi. And V is having three components in the x, y, and z direction, which can be written as ui vj plus wk, where u is the velocity in the x direction, v is it in the y direction, omega is in the vertical direction. Okay, someone want to join? And then we calculated the Coriolis force, which is basically the cross product of 2 omega and v, given as minus 2 omega into ijk. First term is the Coriolis term, which is 0 along the I direction, has the component cos phi along the j direction, sin phi along the k, and then the velocity u, v, and w. And we got it as minus 2 omega into omega cos phi j minus v sin k omega cos phi minus v sin phi along the I direction plus u sin phi k, u sin phi along the j direction plus minus u cos phi k. So this was the Coriolis force component wise. Along the I direction, it has two components, which is omega cos phi minus v sin phi, u sin phi along j direction, and minus u cos phi along the k direction. These are the three different components of the Coriolis force. So if Coriolis force can be basically written as mass into acceleration. So Ma is basically minus 2 omega into omega cos phi minus v sin phi I plus u sin phi j minus u cos phi k. And again, if we are considering a unit mass, or if m is considered to be 1, then we have only acceleration left, which can be written as the differential of velocity, which is du by dt I plus dv by dt j plus d omega by dt k. So are the three components in terms of the acceleration, or as which when we are writing it as the differential of velocity. So we have three components of Coriolis force along the I, j, and k direction. If we write it, it will basically become du by dt is equal to minus 2 omega cos phi plus 2 omega v sin phi. dv by dt will become u sin phi. dw by dt becomes minus plus u cos phi. This will be minus, since it is minus 2 omega. Minus 2 omega velocity. Okay, minus 2 omega u sin phi in case of dv by dt, and 2 omega u cos phi in case of dw by dt. This is how, when we are separating it into different components of acceleration, it will come. Now let's try to solve a problem. So the question is given as calculate the Coriolis force acting on a plane of mass m equal to 5 into 10 raised to 5 kilogram, which is moving from south to north direction at a latitude phi equal to 28 degree north with the velocity 800 kilometer per hour. So we have to calculate F Coriolis. Just write this as F Coriolis. Acting on a plane of mass m. M is given as 5 into 10 raised to 5 kilogram. And the plane is basically moving in the south to north direction, which is in the positive y direction at a latitude of 5 is 28 degree north, and the velocity with which the plane is moving is basically 800 kilometer per hour, or 800 into 10 raised to 3 meter per 60 into 60 seconds. Okay. So now we want to find the Coriolis force that is acting on a plane. So basically the plane is moving. The plane is moving with a velocity v in the south-north direction. The Coriolis force always acts perpendicular to the direction of motion. So since here it is moving from south to north, the Coriolis force will be acting in this direction. And it will be basically in a direction right of the direction of motion, perpendicular to the direction of motion and right of the direction of motion. So it will be acting in this direction. So it will basically make the plane to deviate towards here like this. The Coriolis force will be acting along this direction. So this is basically the j direction. We have v. This is basically the I direction. So we need the Coriolis force which is acting, the I component of the Coriolis force, du by d, m du by dt, which is in the I direction, which is given by, as we have seen here, is minus 2 omega cos phi plus 2 omega v sin phi. So here omega, which is the velocity of the body in the x direction, is 0. So only the second term will come, which is 2 omega v sin phi. So m into du by dt is given by 2 omega v sin phi. Okay. I hope you understood. It is given in the question that the plane is moving in a direction from south to north, which is the y direction. So the Coriolis force will basically act in a direction which is perpendicular to the direction of motion. So if the body is moving from south to north, then the Coriolis force will be acting in the west to east direction, which is basically our I direction. So we have to consider the Coriolis force along the I direction. So that was given by 2 minus 2 omega into w cos phi plus 2 omega v sin phi. So w, which is the velocity of the object along the z direction, is 0 over here. It is only having v component, which is it is moving from north to south. So only v is there. So it will du by dt will reduce to 2 omega v sin phi. That's what we are using over here. So from in this equation, we know the value of 2 into omega is basically the angular velocity of the earth, which is 7.29 into 10 raised to minus 5 into v, which is the velocity of the object, is given as 800 into 10 raised to 3 by 60 into 60. This is done to convert kilometer per hour into meter per second into v into sine phi. Phi is the latitude. That is also given in the question, which is 28. Now, can you calculate and tell me what will be the Coriolis force that will be acting on the body? Or we will just calculate m du by dt. So m du by dt is equal to this is basically du by dt. After finding du by dt, we will find Coriolis. So this is f du by dt. M is not there over here. du by dt is given as 2 omega v sine phi. We know the value of all parameters. Can you calculate and tell me what will be the value of du by dt? Did anyone get an answer after calculating? 2 into 7.29 into 10 raised to minus 5 into 800 into 1000 into sine 28 divided by 3600, which will give a value of 0.013. Okay. Can you tell me the unit? What will be the unit? We basically found du by dt, which will be having a unit of, that is coming around 0.015 or 0.013. What will be the unit? We found du by dt or acceleration. The unit of acceleration is will be meter per second square. So it will be 0.015 meter per second square. We got the acceleration. The question is to find the Coriolis force, which is basically F Coriolis is equal to m du by dt, which will be mass into acceleration. Mass is given as 5 into 10 raised to 5 in the question. So it will be 5 into 10 raised to 5 into 0.015, which will be how much it will be the final answer.
Ma'am, 7,500.
Yes, correct. Around 7,500 kilogram meter per second square. So this is a Coriolis force acting on the plane, which is having a mass of 5 into 10 raised to 5 kilogram and is basically moving in the south-north direction with a latitude of 28 degree north. Okay. So now let's see. So we have learned earlier, like the effect of Coriolis force is to deflect the object from the path in which it is moving. So how much is the deflection? How much is the deflection of the plane in 5 seconds? So if the plane is moving after 5 seconds, how much the plane will deflect from its original path? So we know du by dt. The value of du by dt we know, which is 0.015. So we know du by dt. From du by dt, if we integrate du by dt with respect to integral du can be written as 2 omega v sine phi into dt. Integrate it on both sides, we will get u is equal to 2 omega v sine phi into t. T will come. Integral dt is t. Now du is basically dx by dt is equal to 2 omega v. Now if we integrate it again, we will get delta x or x to be 2 omega v sine phi into t square by 2. We know the value of 2 omega v sine phi, which we found out earlier, was basically 0.015 into t is given as 5, just 25 by 2. How much it will be? How much it will deflect? How much the plane will deflect from its initial path after it has moved 5, after it has traveled for a time of 5 seconds? 0.015 into 25.
0.1875, ma'am.
Yeah, 0.1875. So as the plane was moving from south to north, it deflected a distance of 0.2 meter from its initial path. So it will be now traveling like this. A 0.2 meter deflection has been happened from its initial. So that is the effect of Coriolis force. Let's see two more problems similar to this. Now question is, calculate the magnitude of the Coriolis force by which a train acts on rails the mass of the train is m equal to 5 into 10 raised to 5 kilogram. Its velocity is v is equal to 72 kilogram per hour, and it moves from the north to the south at the latitude 50 degrees. So in this case, now the train is moving from north to south. We know the mass of the train, which is given as 5 into 10 raised to 5 kilogram. V is given to be 72 kilometer per hour, which is 72 into 10 raised to 3 divided by 3600 meter per second. Then 5 is given as 50 degrees. We need to find the Coriolis force. So F Coriolis. Can you tell me at which direction the Coriolis force will be acting? The body is moving from north to south. So the Coriolis force will be acting in which direction?
X direction, ma'am.
Yeah. So it will be acting like this. It will be deflected like this. So along the x direction, as we saw earlier, the component of Coriolis force is basically 2 omega v sine phi into mass velocity. 2 omega v sine phi. So it will be 2 into 7.29 into 10 raised to minus 5 into velocity 72 into 10 raised to 3 by 3600 into sine 50 into mass. Mass is given by 5 into 10 raised to 5. Can you tell me what will be the Coriolis force acting on the body, acting on the train? How much it will be? Did you get?
Ma'am, I'm getting in negative values, ma'am. Is it correct?
Negative values you're getting. Which is actually leading to the negative. Actually, all values are positive, right? This will be the direction of reflection, not the other way around. It will be right. So I'm getting a value of 1115 Newton or kilogram meter per second squared. Just check if it is right or something. I think Soumya is also getting a similar value, like of the order of 1030 is getting, and I'm getting 1115. Just check. I think I don't know if I have made some mistake. If something is wrong, just let me know. I think it is correct. The value is coming around 1115 Newton or 1115 kilogram meter per second square. Just check once again and make sure that I'm not sure if I did any mistake. If I have done something wrong, please let me know. Okay. So were you able to figure it out, Revati? Like why you were getting negative? Okay, I think we will move to the next question. If there is any issue, please let me know. Okay, the next question is, suppose a ballistic missile was fired due eastward at 43° north latitude. If the missile travels 1,000 km at a horizontal speed u0 is equal to 1000 meter per second, by now, by how much is the missile deflected from its eastward path by the Coriolis force. Okay, so now we are considering the motion of a ballistic missile which is fired eastward. So the motion is basically west to east, the u direction, or u is given as 1000 meter per second. So if the body is moving from west to east, in what direction it will deflect?
A y direction, ma'am.
Yeah, along the north-south direction it will deflect. So if it is body is moving from west to east, the reflection will be like this, in this direction. So here u is given as 1000 meter per second, phi is given as 43° north, uh, and distance traveled by the missile x is given as 1000 kilometer, or 1000 into 10 raised to 3 meter. We basically want to find the deflection of the missile, which will be in the direction of y. So delta y we need to find. So in this case, we have to, the Coriolis force will be acting along the y direction. So we need to take the y component, or the Coriolis force which is along the j direction. So when we looked at earlier, so it will be dv by dt. We will be considering the equation dv by dt. dv by dt is given by minus 2 omega u sine phi. So here we will be considering the Coriolis force along the j direction. The y component of the Coriolis force, which is basically dv by dt, is equal to minus 2 omega u sine phi. So again, as we did earlier, we have to find delta y. So first we will integrate this, which will give v is equal to minus 2 omega u sine phi into t. Now if we again integrate v, which is basically dy by dt, we will get delta y is equal to minus 2 omega u sine phi into t square by 2. Now here we know what is the value of omega, which is the angular velocity of the earth, which is 7.29 into 10 raised to minus 5. The value of u is given, which is 1000 meter per second, but we don't know what is the value of t. This is basically the time, the how much time it has been since the missile has been fired from its origin. So basically we need to calculate t. So instead of time, they have given the distance that the missile has traveled. So since we know the value of u, which is distance by time, we can calculate time from here, which is t is equal to 1000 into 10 raised to 3 by u will be 1000. This is basically 10 raised to 3 seconds or 1000 seconds. T is 1000 seconds or 10 raised to 3 seconds. Now, if we calculate the value of delta y, how much it will be? Can you substitute and calculate? We know the value of omega. The value of u is given. Phi is given as 43° north. T we just calculated to be 10 raised to 3 seconds. Just substitute the values and can you tell me the value of delta y or how much the missile will be deflected from its original path?
Ma'am, minus 49.71.
Yeah. What is the unit?
Uh, uh, Meter, ma'am.
Yeah. So it will be approximately minus 50 kilometers. Sorry, 49, the unit will be kilometer, not meter. It will be for 4,900 and something, I guess. 4,971 meter. Am I right? Just check the unit once more. If it is coming in meter or kilometer. Two into 7.29 into 10 raised to minus 5 into 1000 into 10 raised to 3. Because velocity is given in meter per second, right? So it's just 1000 into sine phi. Phi is given as 43 into t. T is 10 raised to 3. T square will become 10 raised to 6 divided by 2. It is coming as 49,717 meter or 49 kilometer. Minus 49 kilometer, approximately minus 50 kilometer it will come. So around minus 50 kilometer, it is coming as minus because it is in the minus x direction. Sorry, minus y direction, which is north to south. South to north is positive and north to south is negative. So the negative is coming because the deflection is in the negative y direction. So it is coming around minus 50 kilometer. Please check the unit. It will be minus 50 kilometer approximately. So around this much the ballistic missile is deflecting. Now let's have a look at a smaller scale motion or like throwing a ball or something like that. The things that we do on our daily basis. So suppose if a baseball player throws a ball at a horizontal at a horizontal distance of 100 meter at 30-degree latitude, 4 seconds, by how much it is deflected due to the rotation of the earth. we are coming to a motion which is in a smaller scale in terms of length. It is just over a cricket ground. So one guy is throwing a baseball at a distance of 100 meter and 4 seconds, which is basically taking a time of 4 seconds at 30-degree latitude, and how much the ball will be deflected from its initial path. So the latitude is given as 30-degree north, and the distance, they haven't given it what direction the ball is being thrown. Let's consider it to be from west to east or eastward. So let's x be 100 meter, time is equal to 4 seconds. So if it is going from west to east, the deflection will be in north to south direction. The Coriolis force, we will be considering d v by dt, which is given as minus 2 omega u sine phi. So here again, if we integrate it, it will be v is equal to minus 2 omega u sine phi into t, and the deflection delta y will be minus 2 omega u sine phi into t square by 2. Okay, so here we know t, u we don't know. We know the value of omega, which is 7.29 to 10 raised to minus 5. The parameter that we don't know is u, but here we have x and time. So u is basically distance by time, which is 100 by 4, 25 meter per second is u. So can you calculate the value of delta y and tell me? How much did you get?
Minus 0.014.
Yeah, yes, minus 0.014 meter, which will be approximately minus 1.4 centimeter. So I just want to tell you that. So in this case, we saw that. So we calculated the deflection of an object in three different cases. The first case we tried was uh, in case of a plane which is moving uh, from south to north with a velocity of 800 km per hour. How much was the deflection we calculated initially? And in that case, we found the deflection of the plane was around 0.1875 meter. Around 0.18 meter it deflected in 5 seconds from its initial point. So that was the amount of deflection that the plane had undergone. Now then we calculated the deflection that a missile will undergo if it is when it traveled for around 1000 seconds. So at that time we got the deflection as very huge, which is around 50 kilometer. Around like a lot of deflection is seen in case of a missile, which is again at a larger scale of motion compared to that of the aeroplane. And also it has very high speed. And then we finally we calculated the deflection in case of a baseball when we are throwing from one end of the ground to the other end, which is having a very small, like the distance that is just traveling is very in hundreds of meters, and the speed is in meter per second, like in a unit of meter per second or tens of meter per second. So in that case, the deflection was around 1.4 centimeter. So as the scale of motion is increasing, as the object is moving at higher speed, and as the distance that it is traveling is increasing, the amount of deflection that the object is undergoing is also increasing. Whereas in case of a baseball, when we are playing in a ground, the deflection is very negligible. But when we are coming to a larger scale motion like firing a missile and all, then the deflection is becoming very huge. So like for different scales of motion, how the Coriolis force is changing based on the distance the object is covering and the speed at which the object is moving is very much important. So that's what I wanted to say. Now we will just learn. I will just introduce a new topic which is basically known as geopotential. Geopotential. Yeah. So geopotential, what does it mean by? Geopotential is basically geopotential at any point in the atmosphere is basically defined as the amount of work done, the amount of work that must be done to raise an air parcel. Suppose this is an air parcel which is at the surface of the earth to a particular height. Suppose this is set. So this is set is equal to 0. So geopotential is basically defined as the work that must be done to raise an air parcel of mass, suppose 1 kg, to a height of z. The amount of work that must be done to raise this parcel to a height is particularly known as geopotential. So geopotential at any point in the Earth's atmosphere is defined as a work done against the gravitational field. To raise a mass of 1 kilogram from sea level to that particular point. So suppose the geopotential at the point Z is defined as the amount of work done against the gravitational field to raise a mass of 1 kilogram from sea level to that particular point. So the only force that is acting on this particular object is basically the downward acting gravitational force given by mg. So against the downward acting gravitational force, the amount of work that we must do to raise this air parcel from this particular point, which is z is equal to 0, to height z is geopotential at that particular height. So we know work done is basically given as force into distance, F into dz. If dz is the distance between z is equal to 0 and suppose this is dz. This is another layer in the atmosphere, the height z. So dw is given by F dz. And the force that is acting on the body is mg. So dw can be written as mg dz. So here we told in case of the mass of the object is 1 kilogram. So then dw will reduce to dw is equal to g dz. dw or d phi, it can be defined as d phi, or the geopotential d phi is given as d phi is equal to g. This is the equation for geopotential. So geopotential is basically the work done to raise a mass m, to raise a mass of 1 kilogram from sea level to that particular point. So this is the equation for geopotential. D phi is equal to g dz. So now we will just write it in another form. So according to the hydrostatic equation which we have already learned, dp by dz is given by minus rho g. So we will just see at what different ways in which the geopotential can be written. So we just learned d phi is equal to g dz. This is the simplest and the basic form that we learned now. Now let's write it in different terms. So first thing is dp by dz is given by minus rho g. This is the hydrostatic equation that we are already familiar with. So from this, g dz can be written as dp minus dp by rho. And from ideal gas equation, which is P is equal to rho RT, which came from the most familiar form PV is equal to nRT, where volume is given by mass by where density is equal to mass by volume and volume is equal to mass by density. So in this case, mass is 1 kilogram. So P into 1 by rho is equal to N is 1 RT. So P is equal to rho RT. This is a form of ideal gas equation. So from P is equal to rho RT, we can write rho is equal to P by RT. Right? So G dz can be written as minus RT by P into D. G dz is equal to minus RT by P into D. But G dz is basically d phi. D phi can be written as G dz is equal to minus RT by P D. So this is yet another form of the geopotential. D phi is equal to minus RT by P into D. Now if we want to find phi, the geopotential at a particular height z, we can integrate d phi. So now we know what is d phi, which is g dz or minus RT by P d. Now if we want to find the geopotential at a particular height z, we can integrate this from integral 0 to z g dz equal to minus r integral minus p0 to p, where at z is equal to 0 the pressure is p0 and z is equal to z the pressure is p, minus RT by p into d. So if we want to find the geopotential at a particular height z, phi of z is given by integral 0 to z g dz, which is equal to minus integral RT by p d. P0 to p. So this is the equation for the geopotential at a height z, phi of z. So at phi of 0 is basically the geopotential at sea level, which is 0. So that is all about geopotential. Now let's see another two terms, which is geopotential height and geopotential thickness. So geopotential height z is defined as phi of z by g0. This can be written as 1 by g0 into integral 0 to z. Phi of z is basically g this is another, this is similar to the height that we generally use. So in this case, the difference in geopotential height compared to the usual height that we use it considers the change in the gravitational force, change in the acceleration due to gravity with respect to height. So it is a new height parameter, new vertical coordinate, which has been chosen, or which basically considers the acceleration, change in the acceleration due to gravity with respect to height also. So it is slightly different from the actual height that we use. So the geopotential height and the actual height Z is equal when the object is at sea level, because at sea level G is equal to G0. So Z, the actual height that we talk about Z, and the geopotential height Z will be equal at sea level. So that is the geopotential height. So now let's look at what is geopotential thickness. Geopotential thickness is basically the thickness of two thickness between two layers in the atmosphere of two different heights, Z1, Z2. What is the thickness of this particular layer? This is basically calculated as geopotential thickness. So from the geopotential equation we know d phi is equal to g d z is equal to minus rt by p dp, and phi of z is equal to integral. Suppose instead of from sea level, we are considering from a height Z1, the parcel is raised from a height Z1 to a height Z2. The integral Z1 to Z2 g dz becomes integral Z1 to Z2 rt by p dp minus, sorry, p1 to p2 rt by p dp, or phi of Z2 minus Z1 is equal to gz1 minus g become g into Z2 minus Z1 equal to minus integral p1 to p2 rt by p dp. So phi of Z2 minus Z1 by G0. This is basically G0. Phi of Z2 minus Z1 by G0 is equal to minus R by G0. If we divide this by R by, if we divide the whole thing by G0, phi of Z2 minus Z1 by G0 is equal to minus R by G0 into integral P1 to P2 T into dp by p, or phi by G0 can be written as geopotential height at Z2 minus geopotential height at Z1. Z2 minus Z1 is equal to minus R by G0 integral P1 to P2 T dp by the geopotential thickness, or Z2 minus Z1 in case of an isothermal atmosphere, which means the temperature is constant. So we can take temperature out of the integral. So it will become minus RT by G0 into integral P1 to P2 dP by P. So dP by P is basically log. So minus RT by G0 into log P2 by P. So if you want to get rid of the negative sign, it will become RT by G0 into log P1 by P. The geopotential thickness Z2 minus Z1 is given by RT by G0 log P1 by P2. This is known as the hypsometric equation. So the right hand side gives you the geopotential thickness. This is the difference between the geopotential height at two levels, Z2 and Z1. Z2 minus Z1 is given by RT by G0 into log P1 by P2. So we learned three new terms over here. First one is the geopotential, which is basically defined as a work done to raise a mass of 1 kilogram against the gravitational field from sea level to that particular point. It is given by d phi is equal to g dz. Then we learned geopotential height, which is given by phi of z, geopotential by G0. So this is actual height because here we are considering the change in the acceleration due to gravity with respect to height as well. So it is given by 1 by G0 acceleration due to gravity, acceleration due to gravity, acceleration due to gravity, acceleration due to gravity into integral 0 to z g dz, where in here g will change with respect to height. G is also a variable. G is also variable. So the geopotential height that and the actual height that we generally use becomes equal at sea level when G and G0 are equal. Then we learn geopotential thickness Z2 by Z1 is equal to RT by G0 log P1, which is basically known as a hypsometric equation. These are the three terms that I wanted you to be familiar with. Now let's solve two problems based on the hypsometric equation. The first question, calculate the thickness of the layer between the 1000 and 500 hectopascal surfaces at any point in the tropics where the mean temperature of the layer is 15 degrees Celsius and at a point in the polar region where the temperature is minus 40 degrees Celsius. So basically we want to calculate the thickness between the layers 1000 and 500. So there are two layers. This is 1000 hectopascal and then there is another layer 500 hectopascal. So basically we want to find the thickness between these two layers, which is Z2 minus Z1. And P1 is 1000 hectopascal and P2 is 500 hectopascal. T in the first case is given to be 15 degrees Celsius. So according to the hypsometric equation, Z2 minus Z1 is given by RT log P1 by P2. RT by G0 log P1 by P2. Here the value of R so the value of R is a specific gas constant, which is 287 In case of dry air, we will be using this instead of the universal gas constant 8.314. We discussed how we got this value of 287 in case of dry air. It is previous classes. It is having a unit of 287 joule, Kelvin inverse, kilogram inverse. In case of the universal gas constant 8.314, the unit is joule, Kelvin inverse. So we have converted it in terms of the mass of the gas that we are considering. So 287 joule Kelvin inverse kilogram inverse will be the value that we will be using here. So R is 287 into temperature 15. We have to convert it into Kelvin. 273 plus 15 divided by G0, which is 9.8, into log of P1 by P2. I'll just remove into log of P1 is 1000 by 500, or basically log 2. Can you calculate the thickness between the two layers over the tropics, Z2 minus Z1? How much it will be? What will be the thickness between these two?
Ma'am, 2538.97.
2539.97. I doubt it is the correct answer, that even got a different one. Can you check once more, Revati? Meanwhile, Soumya, can you tell me, did you get different value or the same? Yeah, 5846 is the answer that I am also getting. Please check once again, Revati, if you are doing something wrong. 5846 meter is what I am also getting. So it will be around 5840 meter. This is the geopotential thickness between two layers at the pressure of two layers, one which is at a pressure of 1000 hectopascal and another which is at a pressure of 500 hectopascal. This will be the thickness between these two layers, geopotential thickness between these two layers. The second case is we will have to find the geopotential thickness between these two layers when uh, the temperature is minus 40 degrees Celsius, or we are considering this particular atmosphere above the polar region. So temperature is minus 40 degrees Celsius, which is basically minus 40 plus 273 Kelvin. It will be 233 Kelvin. 233 Kelvin. So if we are considering the atmosphere on top of poles, the geopotential thickness Z2 by Z2 minus Z1 is given by RT by G0 log P1 by P2. And here the difference will be in temperature, which is 233 by 9.8 into log 1000 by 500, which will be, how much it will be? how much it will come in this case over the polar region? What will be the thickness between these two layers? 0.693. What is that? 0.693. The value is coming around 2729. So if we can see, we are calculating the thickness between two layers. We haven't changed the pressure layers that we are considering. Once the temperature is changing. So the initial case, we were trying to find the geopotential thickness between these two layers at a temperature of 15 degrees Celsius, and we got the thickness to be, or it is the distance between these two layers to be 5,846 meters. Whereas when we come over the polar regions, which is at a temperature of 40 degrees Celsius, the distance between these two layers was found to be 4,729 meters, which means the layers have come closer to each other over the poles compared to that of over the tropics. So this is an advantage that we have the actual in case of actual distance, if we calculate the distance, it will be like kind of similar. But here, when we are considering geopotential thickness, we are considering the temperature between the layers also into. We are considering the temperature as well, temperature of the layers as well. So that's why we are getting two different values when the temperature is changing. So one value, the thickness is changing over the tropics and over the poles. So that's why we are using this term, which is basically known as the geopotential thickness. Yeah, have anything to say, Revati?
Ma'am, I have one doubt, ma'am.
Yeah.
Ma'am, in the Coriolis force topic, direction and that force are perpendicular.
Yes. Yeah, the force is acting always perpendicular to the direction of motion.
But how to find whether it is moving positive or negative axis, ma'am?
So it will be towards the right of the direction of motion. Suppose if it is moving from north to south. So if it is moving from north to south, it means the direction of deflection will be in the east to west direction. So I'll show you. So the direction will be perpendicular to the direction of motion, and in the northern hemisphere, the direction of deflection will always be towards the right of the direction of motion. So if the body is moving from north to south, the force will be acting in the right hand direction. So it will be like this. So this is the positive x direction. So so this is basically west to east is positive, and if the direction is east to west, then it is negative. This is a basic convention when we are considering atmospheric motions. So in the initial case, when the body is moving from north to south, the body will deflect in the right hand, like towards the right of the direction of motion. So it will be in the positive x direction. Suppose you are considering a body which is moving from north to south. So if it is moving in north to south, the direction of deflection will be towards the right of the direction of motion, which will be like this. So this is basically from east to west, which is in the negative x direction. Minus delta x it will be, and in this case it will be positive delta x. Similarly, in case of west to east. Understood?
Okay, thank you, ma'am.
Yes. And in the northern hemisphere, it will be in the right. It will be towards the right of the direction of motion, and in the southern, it will be towards the left. It will be towards the left. Okay, that change will also come. In the northern hemisphere, this right side it will deflect, whereas in the southern hemisphere, it will be deflecting towards the left. Okay, so you have to take care of if the motion is actually happening in the northern or the southern hemisphere. That also need to be considered. Okay, I hope it is clear. Now we will move on to some details about the thermodynamics. Yeah. So we are all familiar with the ideal gas law in chemistry. You would all have learned, and you will be familiar with the equation PV is equal to nRT. So this is the ideal gas equation. Where P is the pressure, V is the volume, N is the number of moles, and R is the universal gas constant. Right? Now, when we are using this equation in atmospheric science, the R is having a unit of joule, Kelvin inverse, mole inverse. We are mostly we are interested in the mass of the parcel, mass of the air parcel that we are considering. So instead of R, which is in the unit of joule, Kelvin inverse, mole inverse, we will convert this into in terms of kilogram. We will convert the unit into joule, Kelvin inverse, kilogram inverse. So when we are considering the atmospheric motions, we are mostly interested in the mass of the air parcel that is undergoing the motion instead of the number of moles. So to convert this into, so R is having a value of 8.314 joule, Kelvin inverse, mole inverse correspond to, so 1 mole will be having a mass equal to the molecular mass of the gas. So in this case, suppose we are considering dry air. Dry air in the sense it doesn't have water vapor in the, water vapor is not there in that air parcel. So when we are considering dry air, which is basically composed of 78% of nitrogen and 21% of oxygen and negligible masses of other gases. The molecular mass of dry air MD is basically 78 by 100 into molecular mass of nitrogen, which is 28, plus 21 by into molecular mass of oxygen, which is 32, which will be which will come out to be approximately 28.56 gram or 28.56 into 10 raised to minus 3 kilogram. So 8.314 basically corresponds to 28.56 into 10 raised to minus 3 kilogram of dry air. Now if we want to calculate R, let it be RD, the specific gas constant, which is basically the universal gas constant by 28.56, which is basically the molecular mass of dry air. It will be R star by 28.56, which will be 8.314 divided by 28.56. How much it, into 10 raised to minus 3. How much it will be? It should be approximately 287 joule Kelvin inverse kilogram. So this is a new value of atmosphere using atmospheric science when we are considering dry air. So the issue with the specific gas constant compared to the universal gas constant is that it depends on the molecular mass of the gas that we are considering. So we have one value for dry air and another value for moisture. Moisture, which basically 287 joule Kelvin inverse kilogram inverse. In case of Rm, or in case of moisture, R star Rm will be, or in case of the moisture, the specific gas constant will be R star, which is the universal gas constant, divided by the molar mass of water, which will be 18. So in that case, it will become 8.314 divided by 18 into 10 raised to minus 3. It will be around 461 joule Kelvin inverse kilogram. So in the atmospheric science, we generally use the specific gas constant instead of the universal gas constant. We have already discussed this. I just wanted to remind you of these things. So in case of dry air, so we have to make sure like what type of air we are considering. In dry air, in the sense we are considering a mixture of gases and air excluding water vapor. All other gases we are considering, but the air parcel that we are considering doesn't have water vapor in it. So if we know the pressure and specific volume of dry air are P, D and alpha D respectively, the ideal gas equation becomes P, D, alpha D is equal to R, D, T, where R, D is the gas constant for 1 kilogram of dry air. So PV is equal to nRT, right? So P volume is density is basically mass by volume. So if you are considering we want volume, the volume will be mass by density. So P into M by rho is equal to nRT. So M, we are considering the ideal gas law for 1 kilogram of dry air. So it will be P by rho is equal to R into T, or P is equal to rho R T. We can write P into 1 by rho is equal to RT. This 1 by rho is basically defined as alpha, which is the specific volume of the gas. So 1 by rho is alpha. So P is equal to rho RT will reduce to P alpha is equal to RT, where alpha is the specific volume of the gas. So once we know the pressure and the specific volume of the gas, we can write the ideal gas equation to be P D alpha D is equal to RD into T, where RD is the gas constant for 1 kilogram of dry air, which is having a value of 287 Kelvin joule Kelvin inverse kilogram inverse. This is the value of RT. This is the ideal gas equation for dry air, which is a mixture of gases in the air excluding water vapor. Now the same equation when we are writing in case of water vapor, the ideal gas equation will become EV alpha V is equal to RVT. So the initial equation P alpha is equal to RT reduced to E alpha is equal to RT. E is basically the pressure exerted by water vapor. Pressure exerted by water vapor is generally known as the vapor pressure and is represented by E. Pressure exerted by water vapor is generally represented by E. That's why P alpha is equal to RT reduced to E alpha is equal to RT. So in this case, RV is the specific gas constant for moisture or water vapor. RV or RM is having a value of 461.5 joule Kelvin inverse kilogram inverse. So in case of water vapor, it will become E alpha is equal to RVT, where E and V are basically E and alpha are basically the pressure and specific volume of water vapor. RV is a gas constant in case of 1 kilogram of water vapor. So it is calculated basically from R star by MV, which is R star is 8.314 by MV, which is mass of water vapor, which is 18 gram. So from that we got RV is equal to 461 joule Kelvin, Kelvin inverse kilogram. So that is the ideal gas law for moisture. Now let us solve and solve. Just a second. And let us solve a problem using the ideal gas equation. If at 0 degree Celsius the density of dry air is 1.275 kilogram per meter cube and the density of water vapor is 4.770 into 10 raised to minus 3 kilogram per meter cube. What is the total pressure exerted by a mixture of the dry air and water vapor at 0 degrees Celsius? So the question is, if at 0 degrees Celsius the density of dry air, which is rho d, is given as 1.275 kilogram per meter cube, and the density of water vapor, which is rho v, is given as 4.770 into 10 raised to minus 3 kilogram per meter cube. What is the total pressure exerted by a mixture of the dry air and water vapor? 0 degree temperature, 0 degrees Celsius. The temperature is given as 0 degrees Celsius, which is basically 273 Kelvin. What will be the total pressure exerted by the mixture of these two gases? So according to the Dalton's law, the, to the total pressure exerted by a mixture of gases is the sum of the pressure exerted by the individual gases. So if we want to know the total pressure exerted by a mixture of dry air and water vapor, it is basically the sum of the pressure exerted by dry air, which is PD, plus the pressure exerted by water vapor, which is basically having a notation E. PD plus E is the total pressure exerted by the mixture of dry air and moisture, dry air and water vapor. So initially we will find the value of PD, which is given as rho d RD into T. Rho d is 1.215, and what will be the value of RD? What is RD? The specific gas constant in case of dry air. What will be the value of RD? will be 287. 287 into temperature will be 273. So what will be the pressure exerted by dry air? Can you calculate and tell me? 1.275 into 287 into 273. It will be 998 hectopascal or 99897 pascal. So 100 pascal is equal to 1 hectopascal. So it will be 998 hectopascal. In case of dry air, now if you want to calculate, now calculate the pressure exerted by the water or vapor pressure. What will be the vapor pressure? So in case of vapor, it will be E into E is equal to rho V RV into T, which will be rho will be 4.770 into 10 raised to minus 3 into RV. What will be the value of RV or the specific gas constant in terms of moisture? Yeah. What will be RV?
461.1, ma'am.
Yeah. So it will be 461 into temperature is again 273. What will be the value of vapor pressure in this case? 4.77 into 10 raised to minus 3 into 461.5 into 273. How much it will be? How much will be the vapor pressure?
600 pascal, ma'am.
Yes, 600 pascal. 600 pascal, or it could be written as 6 hectopascal. The total pressure exerted by the mixture of gases will be PD as vapor pressure E. So PD, we got it as 998 hectopascal. So it will be 998 plus 6, which will be total pressure exerted by the mixture of gases is given by around 1004 hectopascal. This is the total pressure exerted by a mixture of gases containing dry air and water. I hope it is clear. Now I would like to introduce one more term, then we will conclude today's class. So it is known as a virtual temperature. So we just saw like dry air and moisture are having different specific gas constants. So dry air is having a value of 287, moisture is having a value of 461. So this differs. So we have to take into consideration what is the dry air or moisture that we are considering. So in order to get rid of using two different specific gas constant, they came with the temperature which will uh, which will like which will compensate for the difference between the gas constants of dry air and moisture. So the value of gas constant for moisture will depend on how much water vapor exists in the air. So the percentage of water vapor that is present in the air is very much important when we are considering the gas constant for moisture, which is basically a combination of dry air plus water vapor. So we should know how much water vapor is present in that particular air parcel that we are considering. Is it occupying 50% of the mass of the total air or 20%, 30%? We should know the amount of water vapor that is contained in the air parcel in order to find the gas constant for moisture. Moisture means it's a combination of dry air plus water vapor. So when we are considering dry air and water vapor individually, we are getting a gas constant of 287, and in case of water vapor, we are getting a value of 461. Now, if we are considering a mixture of dry and moisture, we should know how much water vapor is present in that particular air parcel in order to calculate the gas constant for that particular moisture air parcel. So every time the change in the water vapor concentration makes the mean molecular weight of moisture changes. If the molecular weight of the moisture is changing, we have to recalculate the value of specific gas constant. So rather than using a different gas constant for each constitution of moisture, which means for different moisture with 50% of water vapor, 20% of water vapor, 30% of water vapor, we have in each case we have to recalculate the value of Rn, which is basically the specific gas constant in case of moisture. So since it is difficult to calculate a value of gas constant for each constitution of moisture, the gas constant for dry air is retained and a new fictitious temperature called as virtual temperature is introduced. So in order to solve the issue of using a different gas constant for each constitution of moisture, they came up with by retaining the gas constant of dry air, a new fictitious temperature called as a virtual temperature was introduced. So virtual temperature is the temperature that dry air would need to attain in order to have the same density as the moisture at same pressure. Consider that we have dry air parcel. This is dry, and then we have a moisture parcel. This is moist, which means it has some amount of dry air plus some amount of water. So both are at the same pressure. Suppose both are at a pressure of 1000 hectopascal. Can you tell me what will be the which will be having more density, dry air or moisture? I think we have discussed this before. Which will be having more density? Will dry air or moisture will have more density? Um, which will be more heavier, dry air or moisture? Or you can go back to the question that we just solved. So there we had values of density for dry air as well as density for moisture. Which one had higher value, dry air or moisture?
Dry air, ma'am.
Yeah, dry air have a higher density compared to that of moisture. So rho d is the density of dry air is greater than the density of moisture. Okay, so what we want to do it, we want to make the density of rho d and rho m similar. We should need both should be at a same density. The density value should be same in both cases. Rho d should be equal to rho m. So in order to make the density of moisture to be same as the density of dry air, or in order to make the dry air to have the same density as moisture at the same pressure, we basically have to increase the temperature of dry air. Suppose we increase the temperature of an air parcel, what will happen to its density? As the temperature is increasing, what will happen to the density of an air parcel? Have any idea? As the temperature of an air parcel is increasing, what will happen to the density? Or let me ask you, like, which is more stable, a dry air parcel or moist air parcel? Sorry, a warmer air parcel or cold air parcel. Suppose we have a warm air parcel which is having a higher temperature near to the ground, and then there is a cold air parcel near to the ground. Which one will move along, like which one will rise up actually? The parcel with high temperature or low temperature. Or we have a hot air balloon and a cold air balloon. Which is likely to rise up in the atmosphere? The hot air balloon or cold air balloon?
Hot air balloon, ma'am.
Yeah. So hot, when the temperature of an air parcel is warmer, it will have a tendency to rise in the atmosphere, which basically means it is having a low density compared to that of cold air. So if we increase the temperature of an air parcel, the density of the air parcel will keep on decreasing. Okay. So if we have to make the density of dry air parcel to be equal to that of the moist air parcel, one method is to increase the temperature of the dry air parcel. As we keep on increasing the temperature of the dry air parcel, at one particular temperature, the density of the dry air and moisture will be similar. So at that particular temperature is basically known as the virtual temperature. So we are not changing the pressure at which the parcels are there. We are just changing the temperature of the dry air parcel. So as we keep on increasing the temperature of the dry air parcel, at some particular temperature, the density of the dry air parcel and moist air parcel will become similar. That particular temperature is known as the virtual temperature, and it will be always greater than the actual temperature. So basically we have a dry air parcel and a moist air parcel. So as we already know, the dry air parcel is having a higher density compared to that of a moist air parcel. So we basically want to make the density of both dry air parcel and moist air parcel similar. So to make their density similar, one method is to increase the temperature of the dry air parcel because it is having a higher density. So as we keep on increasing the temperature of the dry air parcel, at a particular point of time, or at a particular temperature, the density of the dry air parcel and moist air parcel will be similar. That particular temperature is known as the virtual temperature. Okay, and this will be always greater than the actual temperature. And virtual temperature mathematically is given as PV is equal to T by 1 minus E by P into 1 minus epsilon. Epsilon is basically RD by R, or the ratio between the specific gas constant of dry air and the specific gas constant of moisture. 287 by 461, which will be around 0.622. PV is equal to T by 1 minus E by P into 1 minus epsilon. So T is the actual temperature and PV is the virtual temperature. Let us calculate the virtual temperature of the dry air parcel that we just used to calculate. So in the previous equation, in the previous question, in the previous question we found what is the we calculated the pressure exerted by dry air as 998 hectopascal, and we calculated the pressure exerted by moist air as 6 hectopascal. So we know what is E and P. So E is 600 hectopascal, 6 hectopascal. PD is 998 hectopascal. So we have a dry air parcel and a moist air parcel. The dry air parcel is having a density of 1.275. The density (1.275 kilogram per meter cube). This is dry. Okay. Then we have moist air parcel. It is at a density of 4.77 into 10 raised to minus 3. So E and PD we know. So this is rho D This is rho m. So we want to make rho d equal to rho m. So the method is to increase the temperature of dry air pass, because rho d is greater than rho m. So rho d should be equal to rho m. Then the temperature of rho d should be higher. So we will find what is the temperature up to which, up to which the temperature of dry air should be increased, so that both will have the same density. So TV is given by T by uh, T into 1 by 1 minus T by P into 1 minus epsilon. This is the equation for virtual temperature. So we know the value of T. It says what was it? 0 degrees Celsius. Just 273 Kelvin. 273 into 1 by 1 minus E is its hectopascal by 998 hectopascal into 1 minus, it is basically Rm by Rd, which will be Rm is 461 and Rd is 287. What will be the value of TV? Can you calculate and tell me how much it should be increased so that we will have Rm by Rd or epsilon will have a value of Rd by Rm, not Rm by Rd, Rd by Rm. It will be 0.622. So 273 divided by 1 minus 6 by 998 into 1 minus 0.622.
Ma'am, 274.09.
274.0. Okay. Yeah, it will be approximately. I think it is correct. I'm getting around 281 or something. How much you got? 273.
274, ma'am.
Okay, 274. Okay. Okay, okay. Just finalize the answer. Like what you're getting, Sami, you're getting a similar value. I'm getting around 281, I guess. Anyway, it is like around that much only. I think it is correct. Yeah. 270, 274. It should be higher than the actual temperature. So it will be higher than 273. 273 is the actual temperature. It will not be lower actually. So 270 is wrong. But 274 is like it could be the answer. 270 won't be because it will be always higher than the actual temperature. Actual temperature is 273 Kelvin. So whatever the value of virtual temperature that you are getting, it will be higher than the actual temperature. So the value should be greater than 273. Okay, 274 or 280 around that much only you will get. 274 or 280. Okay, so that's all about virtual temperature. I hope it is clear. I think with that we will wind up today's class. If you have any doubt, you can ask me or we will meet next week. Thank you. Yeah, thank you. Bye.